All right, so now that we know where our different representations come from for a constant acceleration model, just want to go through like how we'd work with this, and it's kind of because you guys are going to have a couple worksheets to work on, so I'm just going to give you some help with that before you get started on it. So first of all, I'm just going to go through a bunch of graphs that might represent some changing velocities. So suppose we have a cart moving away from a motion sensor and it's speeding up. What would a position time graph look like? It'd look like this. So it's going to get steeper and steeper and steeper. And the velocity time graph would be, well, we could think of slopes like it starts off with zero velocity, ends up with a big velocity, so it's something like this. And that's this. I think this is the really helpful thing to think about is how do those slopes change, and that tells you what the velocity time graph looks like. Okay, let's suppose the car is moving towards the motion sensor, speeding up. So that means it's going to start with a low slope and end with a steep slope, but it's kind of working backwards. So that one will look like this. It's coming towards the motion sensor. And this velocity starting with maybe zero velocity, but ending with a steep velocity, but it's negative. So this graph will look like this. Starts at zero velocity, ends with a big velocity, but it's negative. So this is a motion moving backwards. Cart's moving away from the motion detector and slowing down. So it's starting from, say, position 0, but moving forwards, but it's slowing down. So going from steep slope to low slope. And we can, so in terms of velocity, well, this is positive. That tangent line is positive and big, so something like this, that's positive and big. And it goes to sometime later, it's still positive, but not very big. So maybe something like this. So slowing down. It's always positive velocity, so it's always moving forwards, but it's slowing down. Here we have a cart moving away from the motion sensor. It's slowing down until it stops, and then speeds back up towards the motion. So it's moving away from the motion sensor, slowing down until it stops. So if it stops, actually I was doing this one in red, so I'll do that. It's moving away, slowing down so that it's getting less and less steep till it stops. Stops means it's a horizontal line on a position time graph. And then it speeds back up towards the motion detector. So now it's going backwards and speeding up, so it's getting steeper and steeper and steeper. So that graph would look like it's moving away. So let's just draw some tangent lines. So this first tangent line here, big and positive. This one's a zero tangent line, which means zero velocity, and this is big and negative. So there's our velocity time graph. So working with that'll definitely help you when you're doing this worksheet. This is basically going through scenarios that are kind of like these ones. And to just think a little bit more about what these graphs mean, what does a positive velocity mean for an object? It means it's moving away, it's moving in a positive direction. Moving away from the moving, I'll just say moving away. Positive direction. Negative velocity means moving backwards. If a velocity time graph crosses the horizontal axis, so like there, what does it mean? It means it comes to a stop and it switches direction. That's what happens here, right? This thing was moving forwards, eventually it came to a stop, and then switched directions. That's what's happening at that point. What about the vertical axis? When it crosses the vertical axis, it means that's just the starting velocity. Okay, how can you tell from a position time graph if the object is speeding up or slowing down? Speeding up is the slope is getting steeper and steeper. So that's what's happening here. This slope is getting steeper and steeper. So it is speeding up. Not steep, middle steep, it's big steep. If it's slowing down, its slope is getting less and less steep. That's what happens with this one, slowing down. Nope, that was speeding up as well. Actually, yeah, I'll come back to this. Slope is getting less and less steep, so it's slowing down. This object is also getting more and more steep. It's just in the negative direction, but it is speeding up. And then the last one is, how can you tell from position graph if the object's moving forwards or backwards? If delta x is positive, it's forwards, is negative, backwards. Or we could also say, is the graph trending upwards? Yes, it's forwards. No, it's backwards. Or if the graph is trending down, that's backwards. So this graph here, it's trending upwards, so this is where it's going forwards, and then it's trending downwards, that's where it's going backwards. So that's kind of the relationship for all these. So you may want to jot these down in your notes, it's up to you, or you might want to just refer to this as a study tool or as a reference tool. So whether you want to copy this down or print it off, that's up to you. Okay, now doing some more work with solving problems then. So here's some things you're going to be expected to do. If let's suppose you're told there's a car that's starting at 0, speeds up to say 10 meters per second squared, then slows down back down to 0 meters per second. You could be asked to model this in terms of motion maps, position time graphs, velocity time graphs, acceleration time graphs. So I'm just going to go through this one. If it starts at 0, we could do a motion map like this. So maybe, and then it starts to go back down to 0. So that's the motion map that would represent that motion. Position time graph would look like speeding up, and nope, sorry, goes like this. It's speeding up, then slows down. That's the position time graph for this particular motion. You can tell because the starting slope is 0, because the starting velocity is 0, it speeds up, but eventually it slows down again to 0. So that's the position time graph. The velocity time graph would look like this. It's always moving forwards, so I'm going to draw my axis like this. It's always moving forwards, but it is speeding up. Let me think about this. It starts at 0, and then it slows down again. That's the velocity time graph for that one. So that would be 10 meters per second. And then the acceleration time graph for this would look like it's accelerating forwards and then it's accelerating backwards. So the acceleration graph would look like this. Accelerating forwards and then accelerating backwards. And if you're told it moved a total of, say, 50 meters, let's suppose this is 50 meters, then this area would be 50 meters. So this is something you might be asked to do in some of these worksheets. There's stuff like this. What else could you be asked to do? You might be given a graph like this, an XT graph, seconds, meters, and maybe you're asked to find the velocity at 6 seconds. So then what you do is you draw a tangent line, you get the slope, and that slope is equal to the instantaneous velocity. You could be asked a question where you are given a velocity time graph like this. And you could be asked acceleration or starting velocity. So if you find the slope, that's equal to the acceleration, and the starting velocity would be that right there. So that's the kind of question you might be asked. You could be asked the displacement of this as well. Maybe if you're asked the displacement, so you'd calculate this area. And that'd be the displacement. It turns out velocity time graphs are super useful in kinematics. From the velocity time graph, you can find out the acceleration, the starting velocity, you can get the final velocity, you can get the average velocity, which would be in between those two. You can find the displacement. You can get almost everything from a velocity time graph. The only thing you can't get is you'll never be able to get an initial velocity or initial position from that graph. You'd have to be told that separately. Another question you could be asked could be something like, could be given a graph like this, position time graph, and maybe you're asked to find maybe the average velocity from 0 to 5 seconds. So once again, average velocity is just displacement over time. So in this case, it'd be 10 over 5, be 2 meters per second. So that's another question you might be asked. Yeah. Oh, one last thing you might be asked could be something like this. Here's a velocity time graph. Maybe you're told it moves forwards at 4 meters per second for 2 seconds. And then you're told it goes -1 meters per second for 4 seconds. So the graph looks like this. And you could be asked to find the displacement. So the displacement, once again, is the area between the curve or the graph and the x-axis. So this area is +4 times 2. This area is -1, so you have to consider that's a negative, and this is 4 times 4. So that is -4. This is +8. So the total displacement would be +8 minus 4, so it'd be +4 meters. Okay, so those are some things that you should be able to kind of think about when you work through the next couple of worksheets.